बिस्मिल्लाहिर्रहमानिर्रहीम। आज हम पढ़ेंगे लेक्चर नंबर 10 फैक्टर्स अफेक्टिंग द रेट ऑफ रिएक्शन। तो आज का जो हमारा टॉपिक है वो है फैक्टर्स अफेक्टिंग द रेट ऑफ द रिएक्शन। सो टुडे we will see the various factors that they are affecting the rate of the reaction. Okay, the first factor we have the effect of the concentration. We know that if we increase the concentration of a reactant, definitely the rate of the reaction also will increase. ROR stands for the rate of the reaction. If we increase concentration, definitely there will be also the rise in the rate of the reaction. What do you mean about the increase in the concentration of the reactant? Increase in concentration of reactant means there will be the large number of collision, okay, among the reactant molecules. If there is we can say the greater possibility for the number of the collision taking place among the reactant molecules, so we can say that the rate of the reaction also will increase. If we see the relationship between the concentration and the rate of the reaction, the concentration is directly proportional to the rate of the reaction. If we increase the concentration, definitely the rate of the reaction also will increase. So both are, we can say, that directly related. Concentration depends on the rate of the reaction, and OR also depends on the rate of the reaction. Okay. Now let's take an example. You can see that we have this container. If this container contains the five molecules, 1, 2, 3, 4, 5 molecules. And another container we have that this contains at least 10 molecules. So there are 10 molecules. So the container containing the large number of the molecules, so definitely there will be the more number of the collisions. So here the possibility is greater for the greater number of the collision, and here there will be the few collision, because you can say that the number of the molecules is very smaller, and here the number of the molecules is very larger. Okay, so this container has maximum number of the collision, so that this has the more rate of the reaction. Another factor that we have the effect of the pressure. So we know that the pressure is always equal to F upon a force acting per unit area. So if we increase the pressure, it means the rate of the reaction increase. What does means that increase in pressure? Increase in pressure means if we increase the pressure, the closeness among the molecule increase. We all know that the gaseous molecules that they have very, we can say, the wide spaces among them. So when we apply the pressure, the empty spaces are present among the gas molecules will decrease. So if the empty spaces decrease, so the closeness also will increase, and definitely the closeness brings the strong collision among the molecules. So there will be the more collision, okay, among the molecules. If larger the collision, it means the rate of the reaction also will increase. We take the example, for example, we have the Haber process, that where we prepare the ammonia gas. So at high pressure, that we can know that rate of the reaction increases at high pressure. Another, we have the effect of the temperature. For example, if we increase the temperature, the rate of reaction also increase. What do you mean about the increase in temperature? If increase in temperature means the kinetic energy of the molecules increases. If kinetic energy of the molecule increases, so it means that rate of the reaction increases. So let's have a look at a graph. So this is a graph. On the y-axis, I have the rate of reaction, and on x-axis, I have the temperature. So you can see that there is a linear relationship between both rate of the reaction and the temperature. So this graph is starting from this point is linearly, okay, increasing. Okay, so this is a straight line. So it means that if this value increases, this also will increase. If this increases, so this also will increase. Now we have to take another a graph. So this is, we can say, the relationship between the fraction of molecules, okay, and kinetic energy. So let's understand what's the fraction of molecules. So let's consider if we have a 200 molecules, and among the 200 molecules, the different molecules have the different kinetic energy. If I say we have the 5 molecules, 50, 150, or the 30 molecules, so these all have the different kinetic energy. If I see the fraction uh, of this 30, so 30 by 200, 50 by 200, 150 by 200, so this will be the fraction of the molecules. So we can say that out of the 200 molecules, so 50 molecules have this kinetic energy, the 150 molecules have this kinetic energy. Okay, so this is the fraction of the molecules. Fraction of the molecules means how many molecules out of the total molecules that they are undergoing, we can say, into the chemical reaction, and how many of the molecules that they will form the product. So let's see this graph. This is the graph. So this graph is represented by T1. So this is a temperature T1, and this starts from here, this from this origin, and this goes up, and again it goes down and reaches here. So you can see here, this is, we can say, the smaller number of fraction of the molecules. So this is, we call it, this is the a threshold energy. We call it, this is a threshold energy. This is ET, threshold energy. So here you can say this, the fraction of the molecules is very smaller. But when we have the graph uh, 2, that is at the T2 temperature, so you can see here that the void, the space, okay, between this graph, okay, and this, okay, at this horizontal line, you can see here the space is very big. So we can see that there are the large number of fractions of the molecules here. So at this temperature, so this is the T1, okay, this is T2, and this is the T1. So at this, we can say the molecules have the maximum kinetic energy, and these molecules will definitely form a product. So this is the T1. So these molecules have the, we can say, low kinetic energy, you can say, but they are very, we can say, the smaller fraction of the molecules here. Okay, so this is, we can say, the threshold energy. So all the molecules, that from the reactant side, that they have to cross, okay, this threshold barrier in order to make the product. Another, that we have the factor, that is the effect of surface area. Another point that is related about the temperature. For example, you can see here that the CO, carbon monoxide, is converted into CO2, carbon dioxide, by catalytic converter at high temperature. So today we have the automobile, okay, automobile engines, that we have to see that they have a catalytic converter. So these catalytic converter, actually they function to convert this CO, carbon monoxide gas, to CO2 gas. So this, and actually this reaction takes place at a very high temperature. We can say at a low temperature, this conversion is impossible. So the conversion of CO into CO2 is made possible at this high temperature. So you can quote that where the effect of temperature is noticed. Effect of temperature, we can say, is noticed in the catalytic converter. Okay, we have the fourth factor, that I have the effect of the surface area. So if we have the large surface area, it means that we will have the large rate of the reaction. So both are directly related. Rate of the reaction is directly proportional to surface area. Now take example. If I say that I have this a very large pieces of the calcium carbonate, when this calcium carbonate is made to react with HCl, the formation of the calcium chloride, carbon dioxide gas into the water. But this reaction is very slow, because the larger size, okay, of the calcium carbonate. So these, in actually the atom, that they don't have the large surface area. Uh, if I take the very small powdered form of this calcium carbonate, so this is the CaCO2, this is the powdered form of calcium carbonate. When this is made to react with HCl, so this reaction is very fast. So HCl and this calcium carbonate react quickly to form the calcium chloride, carbon dioxide, and this is the water. Another of the factor number fifth is a catalyst. So what's the meaning of catalyst? Catalyst means which accelerates the rate of the reaction or lowers down the activation energy or provides alternative path for the reaction. Now let's understand graphically. You can see that I have one axis, y-axis potential energy. On the y-axis I have the reaction coordination. Okay, so these are the reactant and these are the products. So if I say uh, this is a reactant, so the reactant molecules that they are the going up and they reach here, this is known as a threshold. This is the ET, this is the threshold energy. When they reach here and again they go down and they form the product. But when we see this is the reactant, if I draw the line here, okay, from this up to this threshold energy, so you can see here the activation energy without the catalyst is very large. So you can see the gap from here and to this point. From this point to this point, you can see that there is a large activation energy, but this gap in actually is without catalyst. Now when a catalyst is added into chemical reaction, now this we can say this we say the huge barrier. You can say that this is the peak. This is decreased. So I have applied here that dot on this graph. So this graph it actually is due to the catalyst. So you have the catalyst. So you can see the threshold energy is decreased. So you can see here from this point to this point, you can see here the activation energy is decreased. So this is the activation energy with the catalyst. If we compare the two activation energy, the activation energy of the reaction without the catalyst, okay, this is the so a wide gap, and the activation energy with a catalyst. So this is the very similar. You can say that the distance. So this in actually graph is a feasible. So we can say that the catalyst and actually they provide the alternative path for the reaction to take place. So catalyst and actually that they have provide alternative, or we can say the way or the path for the reactant. Okay, uh, to form the product. So this is the product.